Hi, everyone. Thanks for being here again today. We're going to go through two short papers from Ken Shoulders that I got from Chris Beskar. Chris Beskar, the CEO of Stevati Aerospace, he was Ken Shoulders' business partner. And this one's the first one is really cool because it's basic EVO questions, and this is a paper that Ken Shoulders did in 2008. So you want to bring that up, Brennan, and we can
Yeah,
start
yeah.
going through it. And everyone in the group here, if you guys have questions or anything as we move along, just jump in and say something. We'll
Okay. Okay. Thank you, Eddie. I'll start reading now.
yeah.
Basic EVO questions by Ken Shoulders, 2008. View of existing science. What I say about EVOs is viewed as the ultimate heretical doctrine by established and entrenched science, because my vanguard statement is that many sacrosanct laws of present single particle physics and baloney when considered from the multi-universe view I advance. For example, neither charge nor mass is fixed in magnitude and energy does not equal mass times the velocity of light squared. In addition, matter, even biological life forms, can be teleported with ease in concealed form at thousands of times the velocity of light.
Wow.
Nuclear transmutation is a trivial act, as many cold fusion workers have already revealed. This descent heresy from from a normal this is descent heresy from a normal existing science point of view. What is an EVO? An entity either containing or being composed of over 1 trillion electrons, which gives them all back to the single electron world upon their obliteration. How is
Wow.
an EV made? They are ubiquitous and usually made of sparking processes. The spark you make by static electricity contains mainly EVOs. Even breaking a rock or rapidly forming a bubble makes EVOs.
Cool.
How is an EVO made? So yeah, I've read that bit.
Yeah.
How are EVOs destroyed? They can be destroyed by contact with a high voltage metallic anode.
Yeah.
What shape do EVOs have? They almost always appear as being spherical when we see their effects. How big are single EVOs? Their size ranges from several electrons to over the diameter of a hair.
Hmm. Interesting.
How are EVOs measured? They can be made to give out either light or electrons and be seen visually. How are EVOs controlled? Very much like free electrons. How do EVOs affect each other? They usually join into superclusters, showing great order.
That's super important right there. Wow.
And
How
aligns
do
with the
EVO
SQK organization. Sorry,
Yeah. No. What was that, Chris?
I said, oh, and it aligns with the self-organization in a way of the SQK, right? Because
Yep.
they kind of self-organized at that point.
Yep. Absolutely.
So sorry to interrupt, Brendan.
No.
right?
No. It's great. Anyone jump in at any time for sure. That's why we're all here. Yep.
How do EVOs affect material? They skate on electrical insulators, but explode conductors into atomic fragments and transmute the fragments.
Wow. That's quite the statement.
What states do EVOs take? I assign a white state to very active EVOs, expressing high charge and mass, and black to vanishing, almost massless EVOs. There are almost an infinite number of gray states between white and black.
Wow, that's interesting too. Huh.
Can EVO states be changed at will? Yes. A device can call a modulator. Sorry, yes. A device I call a modulator can change the EVO state between maximum white to the darkest containable black state.
Hmm. Wow.
What happens to very black EVOs? They disappear completely. The charge and mass vanish.
Hmm.
How fast do EVOs go? From 0 to superluminal velocities in principle, although we presently have no means for verifying the fastest state. Can EVOs interact with normal atoms? They can encapsulate and transport normal atoms to super high velocity at very low propulsion voltage due to the reduced atomic mass.
Wow, that's a mega statement again too.
Can EVOs be used for energy production? Yes, electrical output is achieved by accelerating them at low energy. Sorry, I'll read that again. Yes, electrical output is achieved by accelerating them at low energy cost in the low mass black state and then converting them to high mass white state for high energy extraction by normal electric field induction. Process is then repeated using the same EVO that is rejuvenated and then re-energized.
Wow. You know what? This is that last one we're really going to have to dive deep into. Hey, Chip, going from a black state, converting them to high mass white state for high energy extraction by normal electrical field induction. Wow, that's a statement. Thank you, Ken Shoulders, right? Wow.
That's the barbecue sauce there.
Yeah, exactly, right? And so amazing that we've got this information right at our hands too, eh? Again, thank you, Chris Beskar, for this. You rock. Very,
So we
very
want the
cool.
last one now. The last one is the second one.
It's number one. It's got number one and number two on it. That's the one. Yeah, that's the one we need. Yep. And this is just another short paper. It's just 2 pages by Ken Shoulders. It doesn't say when it was done. The one that we just read said 2008, I believe. So, that's a long time ago, right? But it's typical of military and this type of thing to wait at least 20 years, um, sometimes longer before we find out about these technologies. But you know what? I think in the next year, the Trump back, we're going to find out about stuff a lot quicker. And it's obvious that we're all learning about things as we move along here. So it's amazing.
Okay, so short range electron attractive force by Ken Shoulders. Statement of action. There is an attractive force found between closely spaced free electrons instead of the universally touted repulsive force. This attractive force is effective only at dimensions in the order of atomic spacing, being in the range of 10 to the minus 10 meters, leaving older repulsion laws intact for large spacing. When this force binds two or more electrons, their expressed field at a distance is reduced. This is a newfound property of the otherwise well-known particle. The effect, as shown by many writings of the author, as well as G.A. Messias in Russia, electrons easily cluster into complex structures, having unique properties not available to single electrons. These electron clusters have been named EVs or EVOs by Ken Shoulders, that is, in various papers available for download from this website here.
Yeah.
So it's www.svn.net/KRSCFS/. So in various papers available for download from that website just mentioned, and ectons by the Russian guy Messias. There are several theories for their existence mentioned in associated literature. References, sorry, I'll read that again. There are several theories for their existence mentioned in associated literature references, but a complete description is still lacking. Whatever the effect is that fosters this electron clustering action, it behaves like an unseen substance that enshrouds electron groups, partly masking their charge. It is a short-range force resembling a positive charge, negating the effect of repulsive electronic charge, and can further be defined as a near-field effect that seems to be an innate property of the electron occurring at the time of its creation. This local action is reminiscent of the induction field of electromagnetic theory. This attractive force is a property of the individual electron and not a large group effect. As it extends down in size to electrons, sorry, I'll read that again. This attractive force is a property of the individual electron and not a large group effect, as it extends down in size to electron pairs, as is seen in the electron accretion method of forming EVOs, described early on by Shoulders in an issued patent and the references cited above.
We're going to be going through all of the Ken Shoulders patents. I've got them all as well too. So at some point we're going to get to all that. Yeah. Thank you, Brendan. You can keep going.
Non-discovery sequence. All references cited above show accumulated evidence for the existence of EVOs in various sizes and forms. Seeing the large total of accumulated evidence over such a long period of time brings up the question of how binding it was passed over for a long time, for so long. A citation on how this likely happened is given below. From the earliest realm of electrical investigation using cat hair and amber through the more technically advanced era of silk and a glass rod, it was determined that light charges always repel. What should have been a temporary guideline using this data was erroneously cast in cement as a sacred truth and immutable law by fakirs crying from the scientific tower of Babel. This belief persisted throughout the very technical age of arc and spark investigation, in spite of outstanding but unneeded evidence of the charge accretion. Accretion means, I think, means gaining in mass or gaining in something. Charge,
Yep.
gaining in charge. Charge accretion appearing everywhere in the so-called cathode spot phenomena. The old law of like charge repulsion is good but not all-encompassing, because at any one time there are likely more free electrons adhering to each other in this world than there are being repelled by each other. Electron clusters are ubiquitous.
Wow.
And ubiquitous meaning, just remind me what ubiquitous means. A larger number, is that right?
Yeah, something like that.
Yes.
Large
Yeah,
number
everywhere.
or common. Yeah.
Yeah.
Common. Yeah.
When the electron clustering effect was first found by the author, its mention to all others was treated as scientific sacrilege, as the message from the fakir was still echoing through the halls after these many years. The message here is believe your own senses tell. Sorry. The message here is believe what your senses tell you, and not what others say.
Wow. Awesome.
What I see is that the like charge between electrons more often attracts than repels. Whenever the spacing between them is small. So the reference here is number one reference is explosive electron emission by AGA Messiat's Isbin number. That number there. Euro Press. I can't. Yeah, Teringberg. Can't pronounce that word.
Yes.
Okay. This
Wow.
one.
That's
This one here.
yeah. That's the last one.
And what a paper.
Yeah, no kidding, right? Super revealing. And once we get done here, I've got a thought about some research that Brendan has done already that we can look at that refers back to this, I think.
This is profound.
Well, when I
Yeah.
do my PhD in subquantum kinetics, I'm half joking. If it's possible, I'll do it, but we'll see how it goes.
Somebody needs to. Yep.
Can EVOs be used for propulsion? Yes, propulsion is achieved by using only half the energy production cycle in what is called mass rectification, by which the EVO runs white in one direction and black in the other,
Wow.
resulting in unidirectional thrust generation without any mass being lost from the system.
Holy cow.
How large can EVOs be made? Unfettered growth results in unstable or potentially explosive EVOs above a size of about 0.1 per millimeter. Ordered growth of arrays has no known upper size limit.
Hmm.
Are EVOs harmful? They readily penetrate any material when in the black state.
Yeah.
If excited from the black to the grey or white state, while within a biological specimen, they give off a harmful electron shower whose damage resembles nuclear radiation. When a single white EVO state strikes a biological specimen, it feels like a small shock or sting. Interaction with solid material as in solid state cold fusion reactions produces a form of uncontrolled EVO radiation that cannot be shielded and is potentially harmful.
Wow. Part of the reason why actually I'm doing all of this stuff with Ken Shoulders and sharing it with everyone is because of that last statement. We need to make sure that when people do research that it's safe. And Chris Beskar told me that Ken Shoulders' cancer, which was all through his body, was they thought was caused by this, by doing research. So that's why we need to learn about the black and the white and how they change from state to state and make sure that everyone is safe doing this. So
This is the strange radiation that Bob Greener
yeah,
talks
yeah,
about.
exactly.
Yeah.
Yep, exactly. Strange radiation. Yep, that Bob Greener talks about. Yep, exactly.
Can weapons be made using EVO technology? Absolutely. Weapons are the easiest use for EVOs that can be visualized at this time. Is there a way to protect against EVO weapons? There appears to be a kind of shield possible, but it is difficult to do.
We're going to have to ask Chris Beskar about that directly. I'm going to do that, actually.
Can large
I think Bob
objects
Greener has, sorry, I think Bob has a sort of shield that he uses, but I think it's a layered organic and metallic material like a orgone collector, something like that.
Okay.
Is
Yeah,
what I
because
believe it might be.
they had stuff set up during the experiment, when they're trying to do the John Hutchison stuff, and they did have some shielding. I was wondering what type of materials that they were using. Yeah, very important. Sorry, Brendan, you can.
Can large objects be covered with EVOs? That appears possible by essentially knitting EVOs into a form of blanket used
Wow,
for completely covering sequestered physical objects.
wow.
Would the properties of sequestered objects resemble those of EVOs? It is thought they would.
Hmm.
Would sequestered objects have low mass and superluminal properties? It would seem so from measurements on small groups of particles.
That's an awesome statement itself there too, right? Oh,
Would these objects be visible? Not while the EVO sheath was black. Would
Close.
would this ensemble run into things and break? No, it would pass through objects with only minor physical contact.
that's crazy. It almost sounds like phasing through something, right? And I think that's what they're
Photon.
doing.
Yeah.
Yep, yep. Wow.
Would contact be possible with presently unseen objects? It is possible that an entirely new dark matter world exists that could be discerned from this new EVO dais or podium. Space is literally filled with things we cannot see from our limited vantage point.
Wow.
EVOs will give us a whole new vista of what does not appear to us in this dark form. So EVOs will give us a whole new vista of what does not appear to us in this dark form. Okay, that's the end.
It's almost like getting glasses and seeing something completely different that you never saw before. And that's what we're diving into. Like some of the statements in both of these papers are incredible. Hey guys.
Yeah, amazing.
Brendan, you know that simulation, the 2D simulation that you did of the solitons, the Turing wave? Maybe you can bring that up and show it to the group, because in the first part where they're talking about how they, attract and repel, I think we're seeing it here. See, they attract and then they repel, right?
They're accelerating down one gradient for this side and one gradient for the other side.
Yep.
These are a Ethron gradient, a G gradient.
So are they wells then? Explain that a little bit more.
So the gradient, one side the gradient's like that, the other
Yep.
side the gradient's like that, and there's a gap in the middle. There's a parallel, a kind of line in the middle. So that it's in 2D. So the gradient's in 2D, and the particles start up here and they roll down the gradient. They
Right.
accelerate down the gradient.
And when you did this, you had to intuitively sort of work with the numbers and the factors to actually make them stable, right?
I mean, Lumi had written this code. Lumi was a guy from Finland who has worked with us for a few months. He was a youngish guy, woman. Sorry, it's woman, not a man. Yeah, but and he was he had done theoretical physics BSc, and he had done a master's degree in fluid dynamics.
Oh, well, that's
So
interesting.
he was a programmer. He worked in AI, and he's a programmer.
Oh, wow.
So he had written the code. I mean, I don't know if he had it beforehand or whatever, but he seemed to write it in about 2 weeks or whatever. And then he just had one large soliton stationary, and he was trying to get it to move anyway. He left the group. We wanted to do other things, and he still looks at the Facebook page sometimes, I noticed. But so then I took that code, I adapted it. So I made the soliton smaller, the canvas bigger, and the soliton smaller.
Yeah.
And then I managed eventually to get a gradient. And Paul was very happy with this. So I managed to put a gradient in there. It converted it, a 1D gradient, into 2D. You see, this is a 2D image.
Yep.
The Z-axis is the concentration, the X and the Y is space. So it's a 2D surface plot, basically.
Yeah.
And then I was looking around as I just sort of played around, and then finally I found I could accelerate them. We didn't know they would stick together. I mean, the fact that when they collide, they actually kind of maintain their integrity. They don't fall apart.
Yeah.
It almost looks like
he was telling a friend of his they're bouncing off each other like billiard balls.
Yeah.
And this is reaction to fusion. So there's the X, the Y. If we deal with them as substrate. I mean, in reality, there would be like trillions of ethrons making up the particle.
Yeah.
This is more like a kind of cylinder. This is more like we're simulating cylinders, in a way. But it's one way of looking at it, you know. So,
Brendan,
go on.
question. This positive negative reciprocation is the built-in pump that we're looking for at an atomic level. You know, Dave Rossi talks about this a lot.
Yeah.
And I find this reciprocation as a firmament pump of sorts. Here we are at a single atom capability to reciprocate and create this subquantum pump. So what math did you use to actually create the positive attractive force that then reciprocates to negative?
The positive attractive force, what we've done is in subquantum kinetics, you've got reaction to fusion. So you've got concentration. So the Z-axis is concentration, number of ethrons per unit volume as a substrate. So it's just an arbitrary number, just giving it a substrate value.
Right.
So it's just an arbitrary number. In reality, it would be like trillions of ethrons, but we can just treat them as a substrate reaction. Fixed law of diffusion in chemistry. You can deal with
I see.
concentration, concentration. Just give it a value like 2 or 3. But the computer model takes it to a certain level, right? So basically, it's gone.
Going back to the Feynman letter,
he
missed that basic concept that you're demonstrating here.
Exactly.
He missed the fact that an electron cluster could be positively charged and therefore attractive at certain distances.
Yep.
So where the hell does that come from? Why is it that Coulomb force everybody understands? Why is it that certain species, these things are attractive? Where does that positive charge come from? And let's not lean
Charge,
on source for this one.
Justin, we're looking at Justin talks about looking at it physically. He says that the conventional physics is more mathematical. It's more the maths is not. So what's Paul doing is a kind of sub-quantum level. We're looking at something that looks maybe a bit like a neutron. This is a kind of neutron-like particle. These two particles here.
Okay.
So as rings. So but they're rings of X, Y, and Z. Sorry, X, Y, and G. So you've got the Y ethron, you've got the positive and negative pole of the X and Y etherons. And then and it's a soliton, and then you've also got the G etherons in there as well. Another wavy
So
ether.
essentially the model that we've used for a couple decade or 200 or 300 years of an atom is wrong.
Absolutely. Bingo.
This is where the secret comes from.
Yep.
We don't understand how they can be both black and white, positive and negative, at certain scaling variations. You would think it would scale linearly across all size and spacing considerations. That is not the case. The system is completely nonlinear.
Yep.
And hence, like a soliton, these damn things can pass.
These are nonlinear, and also,
yeah.
What's his name? De Broglie had difficulty when you know. I don't know if you know how much you know about quantum theory, but when the particle, the kind of like a particle, the wave function. I've forgotten the name of it now, but the oscillation of the kind of pulse that de Broglie was looking at that represents a particle, a wave function of a wave of a particle.
Right.
He realized they couldn't maintain itself. It kept falling apart. It kept dissipating away. That's why you've got time evolution in quantum theory. They try and piece it together so he realized he needed to be non-linear. Paul's done it with this sub-quantum model is non-linear.
Yeah.
Non-linear reaction to fusion.
Brendan,
but the soliton maintains itself. It holds its integrity together. That the quantum particles, the quantum mechanics particles, they try because in quantum theory, in particle physics, they use classical physics a lot of the time. So only when they're measuring something or looking closely at something, they use quantum mechanics. For a lot of the time, they're just using classical physics to do the work. You know, they just use quantum. From what I understand, they use quantum mechanics from time to time to sort of like when they're measuring something or whatever. You know, so de Broglie couldn't get his particle to sustain itself. It kept dispersing away.
Yeah.
And he realized he needed to be non-linear. But he didn't know anyway, he didn't know how to do that.
To answer your question a little bit, Chip, also, there are 5 differential equations that come out of subquantum kinetics. So, Brendan, are those equations being used in this simulation?
Yes, those equations are being used in the simulation.
Yeah, so there's your answer.
So these equations here. So Paul is using a sort of minimal amount of mathematics. All you need to know in subquantum kinetics, all you need to know basically is 5 different equations, because in conventional physics you've got millions of equations. Millions of equations.
And that's the beauty of subquantum kinetics too, is it's very pure.
In subquantum kinetics, you've just got these 5 kinetic reaction kinetic processes. That's the chemistry symbolism.
Yep.
Each one of these letters it represents concentration, number of etherons per unit volume as a substrate. Okay, so when you come down here, you got there. He's looking at ellipsis. If I can find it.
So one or more of these equations, or all of them taken as a whole, predict this reciprocation of charge of the electrons, and hence probably the transmutation flavors of quarks at a subatomic level. where does that physical process, what is it founded on that we're varying the charge of an electron based on the scale of the system? Does anybody explain that? We can throw every damn differential equation in the world at it. If we can't come up for a physical explanation, then it's difficult to, we can't even test it, right? But
Paul is talking about an explanation for charge. He says in conventional physics, they don't know what charge is. They're just giving it a name. They don't
Yeah.
even what's his name?
I agree.
They don't know what it is. Even what's his name? The guy who wrote Elegant Universe, the string theorist. Can't remember. Brian Greene says, "You ask me what is charge. I don't know what charge is. I mean, I believe it exists. But if you ask me what is charge, I don't know what that is. You know."
Yeah.
So, but we can measure it and we can put it in equations, but he don't know what that is. So Paul is coming more from a physical perspective.
Thank
Conventional
God.
physics is coming more from a mathematical perspective. You
Yeah.
know, so
So what if part of the reason, we discussed this and with some of this crazy stuff I've been talking about with cork spin, etc. I would contend that maybe Brian Greene doesn't know what the hell charge is or how it's used, because cork spin may be intimately involved. And I could see the same engine room here. We're transmuting an electron with spin variation. And that creates a fluctuation. I can't get on board with charge either. What the hell is taking charge from positive to negative and creating this natural reciprocating system that probably operates at terahertz frequencies?
Yeah.
What is creating that charge variation?
And what I know about it is Paul talks about charge, which would be in space-time, and virtual charge, which is in time-space, right? So where does it come from? It comes from the other side, essentially, right?
and we're talking about so we're measuring it. We're doing everything with diffusion, reaction and diffusion. So we're
Yep.
just doing constant, and that's measured in terms of concentration. So if you've got a high concentration here, a low concentration down here, then the ethern's going to flow down. They're going to diffuse
Yep.
down. And that's reaction. I was saying concentration produces motion. And Lumi said, no, reaction diffusion produces motion. So we're just dealing with the motion, the reaction and diffusion of etherons. You can produce this soliton. And
Yep.
just like Feynman said in Paul's book, I mean, I can get you up here what Feynman said,
Yeah.
which Paul may have got the idea for calling them exons from Feynman.
Oh,
So Feynman in his book, Feynman Lectures on Physics, I've got his 3 volumes on the shelf over there.
you
In
showed
their
me one
book,
of those
Feynman
before,
Lectures,
yeah.
in their book, the Feynman Lectures on Physics, 1964, Feynman, Leighton, and Sands comment on the infinite energy absurdity of classical electrostatics, and suggests that it could be eliminated by postulating the existence of an underlying reaction diffusion medium. They discuss the example of neutrons being generated in the core of a nuclear reactor. As the neutrons diffuse radially outward through the reactor's surrounding graphite medium, they produce an inverse square flux field that has precisely the same mathematical properties as the electrostatic force field around a charged particle.
Wow.
Feynman et al. Speculate that the electrostatic equations of physics may just be simplified macroscopic descriptions of the collective behavior of hidden microscopic world engaging in such reaction diffusion processes. They ask, could it be that the real world consists of little exons? Paul got the idea of it. I may have got the idea of exons. So he discovered this after he created subquantum kinetics. He discovered this thing, Feynman. Could it be that the real world consists of little exons, which can be seen only at very tiny distances, and that in our measurements we are always observing on such a large scale that we can't see these little exons? Paul calls etherons exons and muons for electric field and geons for gravitational field, and that is why we get the differential equations. So we can't see these electrons, and that's why we get the differential equations. Our currently most complete theory of electrodynamics does indeed have its difficulties at very short distances. So it is possible, in principle, that these equations are smoothed out versions of something. They appear to be correct at distances down to about 10 to the minus 14 centimeters, but then they begin to look wrong. It is possible that there is some yet undiscovered underlying machinery, and that the details of an underlying complexity are hidden in the smooth-looking equations. Excuse
Could
me.
he be talking about EVOs right there?
As is so in the smooth diffusion of the neutrons, but no one yet has formulated no one yet has formulated a successful theory that works that way. No one yet has made up a theory of electricity for which this is Gauss's law, first law, Maxwell's first law, but it's just in a different form. This form is a bit different. No one has yet made up a theory of electricity for which nebula squared phi equals minus rho over epsilon zero is understood as a smoothed out. So that's charge density. That's permittivity of free space, and this phi I think is potential. I think it's electric potential. Okay.
Oh.
Okay, I might be wrong about phi. I'll look that up. Is understood as a smoothed out approximation of a mechanism underneath and which does not lead ultimately to some kind of absurdity. So in classical physics and quantum physics, when they go down to the base, they're using classical Maxwell's equations, which are derived from experiment. They're not derived from first principle mathematics. They're derived from experiment, from measurements. When they take it down to the quantum scale, the equations blow up. You get infinite absurdities. So he's talking about this here.
Yeah.
And which does not lead. They have to fudge the equations to make them work.
Yeah.
And which does not ultimately lead to some kind of absurdity. But it must be added, it is also true, the assumption that nebula squared, that's differential of x, y, and z. Nebula squared phi equals minus charge density of the permittivity of free space is valid for all distances, no matter how small, leads to absurdities of its own. The electrical energy of an electron is infinite. Absurdities from which no one yet knows an escape. So that's Feynman writing there. That's Feynman's words there. And then Paul is saying Feynman's speculation about the electric field being similar to the concentration, the same as charge. The Feynman's speculation about the electric field being similar to the concentration of neutrons around a nuclear reactor appears to draw on his own experience from around 1942 of measuring neutrons in and around the core of one of the world's first nuclear reactors.
Wow.
While he was working at Los Alamos, which Paul's father was also on the Manhattan Project as well.
Oh, what?
Paul's father,
I didn't know that.
Paul Aviat's father was working. His mother, I think, was a chemist.
No way. I didn't know
They lived
that.
in Saudi Arabia at one time, I think. I think. While he
Yeah,
was
both his
working at Los Alamos on the Manhattan Project, I think he was the youngest physicist at the time. I think he was about 19 years old at that time. While he was working on Los Alamos on the Manhattan Project, he had been assigned to calculate neutron equations for the Los Alamos water boiler, a small nuclear reactor at the Desert Lab. That was 10 years before Turing had published his seminal 1952 paper on the chemical basis of morphogenesis, and around 25 years before the time of when the Brussels group had first published computer simulations of the bruslator.
Yeah.
So the bruslator is what Model G and subcontinetics is based on. So The idea of reaction diffusion systems and their ability to form spatial patterns was not commonly known at the time. I would suggest that the successful theory that Thanem was alluding to, that no one has yet formulated, is the present model G subquantum kinetics theory that was published 43 years later. The little exons, which he suggested comprised the yet undiscovered underlying machinery, would be the etherons described here, whose activity produces observable fields. Had he known about the bruslator and its ability to generate localized dissipative structures, he may have proposed that a more serious effort be made to investigate reaction diffusion analogues to physical phenomena.
Wow. Brendan, let's talk about Paul's father and mother. I did not know that. Can you tell us more?
He did say when I spoke to him, I thought his mother and father were on the Manhattan Project. He said no, it's only his father. He said his mother was a chemist. Because I was mentioning I lived in the Middle East when I was a kid. When I was a kid, I lived in a Muscat, Oman area. My father was an architect out there between the ages of 6 and 8, about 2.5 years, 2.25, 2.5 years.
Yeah.
And I was mentioning that, and he said my parents lived in, I think either him or his parents or both of them lived in Saudi Arabia for a period. So.
Oh. Do you know what his father did on the Manhattan Project? Was he a physicist or?
He was I think it was a nuclear engineer.
Wow, I did not know that. And his mom was a chemist too.
Yeah.
Wow, that's incredible.
And he was like in the Project Camelot interview, he was doing experiments from an early age, and a chemist set, making a rocket in his backyard. He said he nearly had a very bad accident one time, but luckily escaped.
I remember those chemistry sets actually. Yeah, yep, I do. Wow. Well, very cool. I guess we could probably stop the recording now, and then we can chat more about all this stuff. But anyone has another question before
okay, thank you everyone for watching. Have a wonderful rest of the day.
And thank you, Brendan, for doing this again.
Okay, thank you, Eddie.